Can everybody hear me? The factor? Okay, good. So today and tomorrow, as we end this workshop, and once again, thanks very much for giving me the opportunity to speak, we are going to talk about diffusion in networks and related sort of, you will see immediately that comes along with it some ideas for distributed network algorithms. Okay, so at a high level, we'll be going to talk about this thing called diffusion in networks, and I'll say a little bit about it right now. And we will go along with it. We'll see several examples of distributed network algorithms. So the overview of the 4 sessions is the 2 sessions of today and the 2 sessions of tomorrow. So today we will start by spending the first session on random walks. Okay, how many of you have seen or heard about random walks and done some analysis? Okay, good. Okay, so within random walks, we will see some material that some of you might have already seen, and we will see some material that hopefully none of you have seen. And one of the main motivations of studying random walks and related processes is because they capture a lot of interesting phenomena that happen within networks, whether it's the spread of information, spread of diseases, spread of viruses, spread of innovation, and they actually also are fundamental tools for designing various algorithms, as we will shortly see. In the second half of today, we will see percolation processes. We will cover branching processes, random graph models, and this phenomena called percolation, where we will discuss how certain phenomena happen until a certain period of time, and then suddenly something completely different happens. This is what is called sharp phase transitions or sharp thresholds, and we will discuss some of that. In tomorrow's lectures will be devoted largely to use of things of the kind that we have discussed in algorithms. So we will discuss this thing called rumor spreading and routing in so-called small world network models. We'll talk about navigability of networks, when those certain designs of networks lend themselves to easy navigation. And we will culminate with a study of distributed algorithms for some fundamental optimization problems of the kind that we have already discussed earlier in this workshop, but now focusing our attention entirely on distributed algorithms. Okay, so that's going to be the setup. We will have our problem sessions, and I will try to give out exercises, and it's really important, no matter what you hear it, only when you sit down and do something will you actually realize whether you understand it or not. Anything you work on, I feel there are sort of 3 levels of understanding. One is you read something and it sort of makes sense to you, then you get something. Then you actually try to present this to somebody. That's a little higher level of understanding, which is why many of us like to teach, because that's the only time we actually learn something. Because reading something is easy to forget, but when you actually try to explain something to somebody, that's when you realize that you don't understand half the things you thought you understood. And I think the third level is actually using it in an effective context. So being able to explain it to somebody and then actually using it in a different context. So really the only way to learn, so you might spend the whole day today and tomorrow listening through this, but if you don't really work on related problems and actually do something, you're not going to get much out of it. Okay, and of course it's very difficult to design really nice problems for this, and I'm sure the problems that I will be throwing at you may not be all that very interesting either, but do the best you can, and we will discuss more problems if you have time. I'm here until all of tomorrow, so if you have any questions, we will certainly can talk more. Okay, so we will start with random walks, and I think in all the 4 sessions, what I will do is in the first 20 minutes or so, I will use the slides to give you to lay down the landscape, and then we will use the board so that we can go slowly and go through some of the proofs and calculations that we want. Okay, so the outline for this session is I will go through some basic definitions and notation related to random walks, and we will discuss applications as to why random walks are important. Then we will I will state 2 results, and we will go over these 2 results somewhat carefully. The first result is on mix-in time and convergence of random walks, and the second result is in cover time of random walks. Both of them are somewhat related. We will discuss, there are lots of applications of random walks, and I will mention some of them along the way. We will at the end, we may not be able to go over a lot of detail, but I will explain one use of random walks in clustering really large networks. One of the things that you have to get out of some of this material is what kind of techniques do you need to know to analyze these things, okay? And for random walks, there are two really broad collection of techniques. There is probability theory. Of course, that's natural. Once you're talking about random walks, probability comes in. But one other area that actually you really need to pick up if you want to do advanced research in theoretical computer science, especially in a related field, is spectral graph theory. Okay, we will touch a little bit upon it today, but over time, if this is roughly an area you want to work in, then understanding spectral graph theory is very useful. Okay, so what is a random walk? Well, as you expect, the random walk, and we are talking about random walks on graphs. A random walk on a graph is simply a probabilistic process which describes a movement of a walker on the graph. So you're given an arbitrary undirected graph. You can define it for directed graphs as well, but for today we will completely focus on undirected graphs. A walk starts at an arbitrary vertex v0. At the start of step t, the walker moves from v sub t minus 1. The walker is at v sub t minus 1. And in step t, the walker moves to vertex vt, which is chosen uniformly at random from the neighbors of vt minus 1. Okay? So you recognize that for all t greater than 0, vt is the random variable, because once the walk starts, you cannot pinpoint where the walker is in advance. There is a probability distribution of where the walker is. Okay? So let's look at some notation and then see what are the quantities we would be interested in and what are their applications. So let G be an arbitrary undirected graph and A be its adjacency matrix. Everybody is familiar with an adjacency matrix. Aij is 1. If there is an edge between I and j, it's a symmetric matrix, and we assume that the diagonal entries are 0. You don't, unless there are self loops, in which right now let's assume there are none. So then the random walk matrix can be given by Mij is Aij divided by degree I. The point is that if the walk is at a particular point, then what's the probability that it goes along an edge? It's 1 over the degree of the vertex, right? So that's what the random walk matrix M does. Now, what we will try to understand, we want to come up with a method by which we want to keep track of where the walk is, probabilistically speaking. Okay? So initially the walk starts off at some point, and then over time it changes. So what we will do is we will maintain a vector x that has n elements, where n is the number of vertices, and we will put numbers here, 0.1, 0.2, 0.3, 0, 0, 0, 0.5, and so on. Okay? Yes. Actually, not 0.5. Good.
So there is also a chance of the walker moving back and forth?
Yes, there is. Yes. Okay? So this is what would be called a probability, let me call it as a probability vector. Okay? Now, if initially the walk starts at a particular node, what does this vector look like? 1 at that node and 0 at the node. What can you say about this vector? What statement can you make about this vector that is true at all time? The sum of all the x values is 1. Everybody see that? Okay. Other than that, without knowing more about the graph, you can't say anything else. Okay? Okay. So that's the probability vector. So what we will see, and you should see immediately, that let's suppose the probability vector right now is x. Okay? So okay, let's look at this. Let's say xi is probability walk at I. So let me write this. Did I use any? Okay, sorry. Probability walk at I at the start of step t. Actually, let me make one change. Just to be consistent with what I have before, let me call this xt minus 1I. Question is, what is xt I? What is the probability that at the end of step t, the walk will be at I? Anybody? What is the probability that the walk will be at I at the end of step t? If you start off with...
Is it necessarily moving? Oh.
It is moving, but here I haven't told you that the walk is at I. I've just told you that this is just the probability that the walk is at I, and this is for all I, for all vertices I. What is the probability that the walk is at I in step t, at the end of step t? So what will you look at? For it to be at I, so it has to be at one of the neighbors. So you go over all the neighbors such that, so you go over all j that belong at an edge, right? And what do you do? You look at the probability that the walk is at j at t minus 1 step. Very good. And multiplied by aij divided by d. Aij here is 1 because we assume we are only adding it over those vertices where we have edges. So it's times 1 over the degree of j. Very good. Okay, so so maybe that's a mistake. No, that's fine. Okay. Good. So xti is summation xti minus 1 times 1 over degree of j. So based on this, it's actually not that hard to argue the following. If you write it as a row vector, then you can write down xt is xt minus 1 multiplied by the matrix M. Okay, this will you spend 5 minutes thinking about it, you will get it. Because if you look at x here, this is your vector x, this is your matrix M. Okay, and this gives us a row vector. So the value you get at I is obtained by multiplying this with the ith column. And the ith column is exactly the set of all the j's that are coming that have edges to I. Okay. Okay. So all we are doing is, if we start off with x, what does the random walk do? Is repeatedly take that vector, multiply by the matrix M. That's it. That's what's happening. Okay. Good. So after t steps, the probability distribution vector equals x m to the power of t. Why is that? Well, we take x, initially we start with x, multiply with m, then multiply with m, then multiply with m, and by matrix multiplication associativity, this is simply x times m to the t. Okay? Good. Everybody, any people have any questions at this point? Okay. So, all right, that's clear. So now that we have written it, what can we do about it? Well, for example, you can write a program. Given a graph, you can simulate, you can run the program, and you figure out what happens over time. You can do lots of easy things. But what kind of things are we interested in our understanding of random walks? Well, we want to know whether does this walk ever stop, so to say? Okay. Of course, the walk itself will never stop, but this sequence will keep on getting changed, and we get more and more probabilities of different probabilities as we go along. But we want to know whether is there a situation where I can say that there is a vector pi such that if that's the distribution, then I basically remain at the same distribution. So the question is there a pi such that pi times m equals pi? Okay. The next question is, yeah.
Does not mean that you will reach pi.
Good. All we said right now is there a distribution? I'm going to actually ask these questions. That's a good question. We will see that momentarily. The other question we want to know is if I start from a vertex I, how long will it take for me to hit j? And you can imagine these questions are of interest for spreading purposes. You might want to know if something originates at a node, how long does it take before that influences some other. Cover time, expected time for a random walk starting from an arbitrary vertex to visit every single vertex of G. Okay. And mixing time, we will spend a fair amount of time on this today, is the time it takes for the random walk to converge to a stationary distribution. This is related to this question, does it even happen, for example? We will look at that really. So what are the questions of interest given this? So first question about the stationary distribution pi, does it always exist? If it exists, is it unique? Does a random walk always converge to a stationary distribution? If so, how long does it take to converge to a stationary distribution? Hitting time, for a given graph in vertices ij, what is the hitting time hij? Cover time for a given graph G, what is its cover time? So these are the kind of questions. These are very standard questions, and there are more interesting questions one can, or sort of more non-standard questions people can formulate. But today, for the most part, we will be interested in this. Towards the end, we will look at some other questions as well. So random walks have a gazillion number of applications, so it's really important to understand them, the conceptual standpoints of this. So as you can imagine, they certainly arise in many situations. I mean, they are probabilistic processes whose variance capture lots of social and physical phenomena, economic phenomena, Brownian motion in physics, movement of stocks in a financial system, spread of epidemics in contact networks, spread of innovation and influence in social networks. There are lots of interesting connections to electrical networks. Markov chains, which are a generalization of random walks and Markov chains are almost synonymous. Markov chains are essentially a generalization of random walks arise in numerous scenarios. So those are just viewing the process by itself. But random walks are also very, very effective tools in actually designing algorithms. They are amazingly useful in random number generators. Okay? Of course, random walk by itself uses some randomness, but often you can use a little bit of randomness and generate a lot more pseudo randomness, which is what is often the real source of random bits. So pseudo random number generators, random walk in an expander graph is a very efficient way to generate pseudo random bits from a small random seed. They are used in a lot of different randomized algorithms. We will look at one example of clustering, but volume estimation is another excellent example of where random walks are used in practice. Everybody is familiar with PageRank, right? Google's PageRank, the calculation of PageRank for every web page. That is nothing but a random walk. Okay, how is it a random walk? How many people have heard of the PageRank algorithm? Okay, can anybody say, based on whatever you know, even if you have to speculate, that's fine. Why is the PageRank algorithm nothing but a random walk? And what do you think is it a random walk on? Yeah.
Basically going from one page to the other, clicking on random links.
Yeah.
On the page.
Yes.
So the links could be like edges.
Yes. Exactly. Very nice. So Google's PageRank, the way they viewed it, and it's in hindsight it seems like almost trivial. Really, is that really useful? But when you think about it, what Brin and Page did was they just viewed the web as a graph. Okay, how is it a graph? Each node in the graph is a web page. Each edge in the graph is a link. So then they decided, they felt, if I have to find, the main goal was what are the pages that are important, what pages are not that important. So they decided pages that have lots of edges coming in seem to be important ones, but they should not be coming in from random other pages. They should be coming in from other pages that may also be important. So this is exactly captured by stationary distribution. A stationary distribution basically captures, if I just do a random walk, how often will I spend on each of these nodes? And if you find out, if you do a random walk on the web, you spend so much time on these pages, so much time on these pages, then those pages seem to be important because there are lots of paths leading to them and lots of ways to reach them. So Google's PageRank is nothing but probability vector of the stationary distribution on an appropriately defined random walk. There are a few other engineering things that they do, but that's what it is. Okay? And you can, again, this is often people might refer to it as a Markov chain as opposed to a random walk, but basically they are the same thing. Okay, so our first result we will look at today, we will spend some time on, is the mixing time. Okay, so what we will do is first we will try to understand what does the stationary distribution look like. And the first lemma, which actually directly follows from Markov chain analysis, but we can actually also capture it very easily by a little bit of guessing, that a stationary distribution always exists and is unique. Okay, so let's think about it a little bit. Let's suppose I give you a d-regular graph, that is every node has degree d. Okay, I claim one can easily identify a stationary distribution for this. Okay, does anybody know that? If you know that, if you don't know it, it takes a little bit of time. Does anybody know what the stationary distribution for? Yes, uniform. Okay, so I give it 1 over n to everybody. So I give 1 over n probability to every vertex. That I claim is a uniform, is a stationary distribution. Why is it a stationary distribution? Well, if you remember this, if this was 1 over n, okay, and so this is 1 over n for everybody. This is times 1 over d because it's a d-regular graph. How many edges am I adding this over? D. So that d and this d cancel and I get back 1 over n. So it's very easy to see that if you use the uniform distribution, then it's okay. So that's for a d-regular graph. We will see there is an easy calculation that you can find out another one for a non-regular graph. We will go over that. Okay, what we're going to argue today is that the random walk that, okay, so this is the stationary distribution. Yes?
So just a question, right? So there should be some conditions of the graph, right? For example, if you have just 2 nodes,
Yeah.
any edges,
Yeah.
right? So suppose then there would be sort of 2 stationary distributions, right? Always on one vertex or always on the second.
So that, well, the one thing for the way I have set it up, if it's ill-defined, what happens if there are no edges at all? Okay, it's ill-defined what happens if there are no edges at all. But even in that case, half is a stationary distribution, because if you're at half here, you stay there, half here. Okay, but you're right. Yes. So in that case, depending upon whether it's connected or not, you have an issue. But you're right. Absolutely. Okay. For a connected graph, you can calculate it. If you have different connected components, then you can spend all your time either in one or all your time in the other, and so on. Okay. So what we're going to argue today is that the random walk is within epsilon of the stationary distribution, and I will define what epsilon is in these many steps. Okay, where we are going to use that lambda g denotes the second largest eigenvalue of m. Okay, and if you don't know what the second largest eigenvalue is, don't worry about it. We'll go over that moment. And if it's a non-regular graph, it's a little bit more complicated, but you can replace m by a normalized version of this, and you can go there. Okay, so that's for a heating time. So we will go over that result. We will go over this theorem 1 later today. In order to calculate the cover time, what we will prove is that for any m edge n vertex undirected graph G, the cover time is order mn. So in an undirected graph, whether it's regular or irregular, it doesn't matter. The cover time is just bounded by big O of m times n. There is a nice relationship between cover time and hitting time, and one can prove that the cover time is at most h max, the maximum hitting time between any pair of vertices, times the log of n. And it's actually an exercise, and I would like you to try this out, that prove that the time for a random walk to cover every vertex is big O of the hitting time, the time it takes to go from one vertex to another vertex, the maximum time it takes to one vertex to another vertex, times log n. So big O to hide any constants in case you can't give a tight analysis with high probability. Okay, I'll mention this exercise later as well. Okay, so this is another theorem we're going to go over. Okay, I think at this point, maybe rather than going ahead, we will try to go over these two results, and then we will move on to the other bounds. So let me start. Excuse me. Okay, maybe I'll start working on the board. Okay, so let me move it to the previous one just to see. Okay, so remember M is the matrix. So what we want to understand what happens to, and let's say X is the initial vector. Yes. You cannot see the board?
Yeah, left part.
Aha. Is it because of that or? Okay. Okay. Maybe if these lights are also switched, so maybe you should shut off the. Maybe you can just shut that off and use those lights, because it was visible one. In the lights. Aha.
No, but still it comes.
You can switch it off, and then those lights. Oh, he did the other way.
Yeah, no, it will take a minute, but then.
Okay. Okay.
Yeah, it is visible.
Okay.
And it will become gradually visible.
Okay. Yeah, you can see it's working. Okay, so X is the initial probability vector. So we are trying to look at what happens to X times m to the t. Okay, we are focusing our attention right now on d-regular graphs. Okay, we know these d-regular graphs, the stationary distribution is the uniform distribution. Okay, good. So what you want to know is how long does this take for x m to the t? How far is x m to the t from u? Okay? Good. So what we will do is we want to find out how far they are. So one way you can do is you can use something what's called a 2 norm, or you can look at a norm that captures the distance between the two vectors. So we can look at we can try to analyze this. Okay, what is this? We can define vector y is summation y I square root. Okay? So one way to capture how far are you from the uniform vector is to look at what's the value of the vector minus that vector. Okay, so let's try to see what happens to this. Times m to the t minus u is nothing but x minus u but x minus u times m to the t. Okay? Okay, so basically what is happening is, you think about this the following. Think about x minus u as the initial error vector. Okay? You started off with the distribution x. You really would like to be in the stationary distribution, which is u. So x minus u captures the error that is there in the stationary distribution, because some nodes, so in terms of the probability, you would like everybody to get equal probability. Well, initially you were starting at one node, so it had a 1, everybody else had a 0. So there is excess probability at one node, very little, no probability at the other nodes. That captures initial error vector. But what this m does is you're going from x minus u to x minus u times m to x minus u times m square and so on. Good. So we'd like to know how fast is this going down. Okay, how fast does x minus u, these things go down. Okay, so what can you say? Let me call x minus u as y for now. Okay, so I'm trying to understand what is y times m to the t. No. Okay, this is what I'm trying to understand. Good. Okay, so what can you say about y? What is the summation of all the i's, of all the yi's? 0, because summation of all the x's is 1, summation of all the u's is 1. So this is 0. Good. So let me define my lambda g, or lambda. Let me just use the term lambda. Okay, let me just explain this notation. lambda is the maximum over all vectors that are perpendicular to u of the norm of Zm divided by the norm of Z. This is for normalization. So notice that Z perpendicular to u, what does it mean? The summation of Zi's is 0. So you recognize that this error vector y is actually an example of Z because y is perpendicular to u. So if I define lambda as that, then you recognize that y m is less than equal to lambda y. If I define lambda as the maximum possible value this can take, then I can replace Z by y, then I would get y times m is less than equal to lambda times y. Right? I want to calculate y times m to the t. So y times m to the t, I claim is less than equal to what? Okay, let's do it slowly. Y times m square is equal to y times m times m, right? So ym is another vector, okay? It's another error vector. In fact, that summation of all the y's is also 0. So this is less than equal to lambda times ym. That we know is less than equal to this, so that's less than equal to. Yeah. Good. Perpendicular means the dot product of z and u is 0. Okay, perpendicular means z dot u is 0, which is the same as summation 1 over n times zi equals 0, which is the same as summation zi equals 0. Okay? Okay, so ym to the t is less than equal to lambda to the t. Sorry. Okay? Now you can recognize the value of this. I mean, it's not this is a less than equal to, so it's not obvious that it's capturing everything there is to be. But let's try to understand this. We started off with the error vector y. If we repeatedly apply the random walks vector, then our error vector becomes y times m to the t. And we notice what happens is that if you start off with error vector y, it has a certain length. This is just captured by this. Then the length is repeatedly being multiplied by lambda. So we would like this to become very tiny, right? We want the error vector to be very, very small, meaning very close to epsilon. So what do you think we would like lambda to be? So we're starting off with some error vector. We want it to be over time. So our error vector originally is y, and it has the length of this. Then we go to lambda times y, lambda to the t times y. Okay? So we would like it to be small. So what do you want your lambda to be? Less than 1 at the very minimum, right? We want it to be less than 1. So if it is less than 1, then you know that it is sort of going down. But how much it is less than 1 will decide how fast it goes down. So that is basically the point. Random walks are very, very well captured by how small this lambda is. It turns out this lambda, and we will also prove it in the next 5 minutes hopefully, that this is exactly the second largest value of m. Second largest eigenvalue of m. Okay, I might just quickly do the calculation because it does require some background. But Okay, but before doing that calculation, let's try to look at this a little bit more closely. Okay, this quantity. Okay, so it is maximum over all z perpendicular to u of the quantity z times m divided by z. Okay. Let's consider let's see. Okay, so let's suppose I give you a bipartite graph. By the way, one thing I want to emphasize here is we are notice that all of this statement is independent of where you started off from x. You're saying no matter where you start off from in this many steps. So we haven't said anything about steps. So we've just said that if lambda were small, then we are going to get closer and closer to the error vector. Okay. So let me go over that first. Maybe how long does it take? Okay. Initially, suppose want to find t such that okay, we recognize that initially the error vector is no more than 1, because remember none of the entries so some of the entries is 1, so the sum of the probabilities is 1, so you can actually give that bound fairly. Let's see. So if you have, this is the sum of the you can calculate. Let's suppose we want to find t such that I'll make a change to this momentarily. I want to find t such that every entry in y is less than or equal to epsilon. Okay, I want to find is less than epsilon over n. Okay, so what the uniform vector is 1 over n. I want to find how long does it take before I reach the entry which is something like 1 plus minus epsilon over n. This is what I would mean by I'm getting close to the uniform distribution. Everybody happy with that? Because I want to get 1 over n. I cannot guarantee that I will always reach exactly 1 over n, because it'll take an infinite amount of time depending upon where I start from. But I want to see how far will it take before I get close to 1 plus minus epsilon over n. If it is less than or equal to 1 plus minus epsilon over n, then what can you say about the error vector y? What will be each entry in the error vector? Less than or equal to a plus minus epsilon over n. Okay, so it's within plus minus epsilon over n. Then at the end, so this is the error vector at time t. So what will be the norm of the error vector at time t? Okay, so this will be, I claim, is less than or equal to square root of epsilon square over n square. Right? Because each entry is no more than epsilon over n. So what is this equal to? Sorry, n times, thank you. So what is this equal to? epsilon over square root n. Okay, so I want to go from something that starts off with at most 1, I want to go down to epsilon over square root n. So how much is the ratio between the two? Starting from 1 to epsilon over square root n. What is the ratio? Square root of n by epsilon. So ratio, so this should be epsilon over square root n. So ratio is, let me do the calculation here, ratio is square root of n over epsilon. How much am I decreasing, what factor am I decreasing by every step? Lambda. Okay? So if I'm decreasing by a factor of lambda every step and I have to bring down by a ratio of square root n over epsilon, how long will it take?
Lambda power t is equal to square root of n by epsilon.
Excellent. You want lambda to the power of t should be equal to or greater than equal to square root n by epsilon, which means you want your t to be equal to what? Log base lambda of square root n by epsilon, which can be written as log n over epsilon divided by 1 minus lambda. Okay, ln of lambda is roughly 1 minus lambda for lambda less than or equal to 1. Okay? Okay, one thing I should say is, no, I think that's fine. That's correct. I should have actually said that, here we are assuming that lambda is positive. We are taking the magnitude of lambda. By lambda we are referring to as the magnitude of lambda everywhere. Okay? Okay. So that gives us this bound that I have written here. Okay, where did the square root n was just replaced by n, because you see that log of square root n and log of n are about the same, right? They differ by a factor of 2. Log of square root n is half of log n, and since I have hidden that in the big O notation, none of that matters. Good. So now really the question now becomes, so if you ever have this question, how long will this random walk take to terminate or to reach a stationary distribution? Often all you need to look at is what is lambda for that graph. The lambda for that graph. So it's really beautiful. One number for the graph captures a lot of information that you wanted. And this is really the beauty. This is the beauty of what's called spectral graph theory, because you can capture with some, you cannot capture everything, of course, because the graph has its own, there are lots of different properties, but certain numbers associated with the graph tell you a lot about the graph. Okay, so let's try to understand this lambda a little bit more. Let's try to take an example. Let's try to calculate it for a bipartite graph. Okay, let's for now let's make our life a little bit simple. You have okay, actually let's do it even simpler. Let's just do it for a 2-node graph. Let's say you have a 2-node graph. Okay, that's it. What is the M for this 2-node graph? 0, 0, 1, 1. Okay. So I want to maximize Zm divided by Z such that Z, of course, the sum of the Z's should be perpendicular to you. Okay. So if the Z's have to be perpendicular to you, basically you have to give one number to one and minus one to the other, minus of that to the other. So basically I only have one choice, which is 1 and minus 1. Okay. Okay, so that's the only choice. So if I take 1 and minus 1, so I put 1 here and minus 1 here, then I just multiply 1 minus 1 times 0, 1, 1, 0. What do I get? This is 0 minus 1. 0 minus 1. This is 1 minus 1. I get minus 1 and 1. Of course, it's obvious, right? If you start from 1 minus 1, you just flip it. Minus 1 and 1. Okay. What is ZM of that? Well, Z equals 1 plus 1 square root of 2. What is Z times M? Also square root of 2. So what do you get your lambda to be? What do you get your lambda to be? 1. What is this theorem saying? That the stationary distribution terminates in order ln of n over epsilon divided by 0 steps, which means this is going to take an infinite amount of time, which is what you want it to be. Because in a bipartite graph, you can never reach a stationary distribution if you start from certain situations. Because why? You will always be either in the odd side or on the even side. You will never reach a point when you will always be either 1, 0, the probability is either 1 and 0 or 0 and 1, so you will never reach a stationary distribution, even though there exists stationary distribution for this graph, but you may not reach it. Since this theorem is about reaching stationary distribution, no matter where you start from for a bipartite graph, we should really get the answer that you may never reach a stationary distribution. Okay? So one thing you should be able to argue is that for any bipartite graph, you can actually identify, notice that this is the maximum over all z's. You can identify a z perpendicular to u such that zm is equal to z, and you will get always you get lambda to be plus 1. Okay, so one exercise for you guys is that calculate calculate lambda for complete graph. Okay. Do you think lambda would, for a complete graph Kn, would be very close to 1 or very close to 0?
It's independent of t, right? The lambda is
D is a degree? Yeah. So it depends. I mean, here we are assuming.
not the deregular graph.
Here we are assuming a deregular graph.
No, for the bipartite example.
Yes, it's true, independent of the degree.
Degree.
Yeah. Yes. Yeah. It will be close to 0. Okay, so try to calculate what it will be. Why will it be close to 0? Well, intuitively, the closer to 0 it is, the more rapidly it mixes. And you would think that in the complete graph, it should mix as fast as you possibly can. Okay. The expander graphs are those graphs in which every set of vertices has a lot of edges going out of it. Okay. Okay, let me state it. So expander graphs are those graphs. Let's call it, let me give you the formal definition. For all sets, subset of V, size of S is less than or equal to n over 2. The number of edges going from S to V minus S divided by the size of S is greater than or equal to alpha. So this is called the expansion. Okay, expander graphs are constant degree graphs with, so think of it as big O of 1 degree with omega 1 expansion. Okay? Yes, will be at least some constant, yes. Okay, notice that alpha cannot be, if you assume it's a constant degree, by the way, I should define this notation. This is the number of edges going from S to V minus S. So the number of edges going from S to V minus S can be no more than D times the size of S, right? D is the degree. So this cannot be more than D, the degree. And I have told you that the degree is a constant. But you can actually make sure that you can build expanders in which every set, no matter what set you look at, has a lot of edges going out of it. Okay. Now when you have these graphs in which no matter what set you look at, there are lots of edges going out of it, intuitively random walks should mix very well. Because no matter where you are, your random walk will not get stuck because there are so many places to move out. So you would expect that your lambda should not be very, very close to 1. And indeed that's true. For expander graphs, lambda is also a constant. Lambda is strictly less than 1. Is a constant strictly less than 1. Is O1 in this case. Okay. I should say some constant actually. I should just say some constant. Okay, and again you can prove all these by looking at this thing. It's not that hard to prove all of that by looking at this particular calculation. Okay. Okay. So let me show you the connection with eigenvalues. So this is really the second largest eigenvalue. Let me show you the connection with that. How many of you are familiar with eigenvectors and eigenvalues of matrices? Okay, good. Again, if you're not familiar, it's not. This is something which is, of course, there is a huge piece of mathematics behind it, and it takes a little while. It's often easy, not that hard to understand the symbols and what they really, what the formulas look like. It's much harder to get an intuitive understanding of it, and that I think you can only get by doing a lot more of these examples and exercises and seeing the connections. But if you look at this M, our matrix M, okay, it's a symmetric matrix, real valued symmetric matrix, so it has a set of eigenvectors and a set of eigenvalues. So let's write down its eigenvectors. So let's call its eigenvectors V1, V2, Vn. Yeah. Good, very good question. But we are looking at deregular undirected graphs. For a non-regular matrix, for a non-regular graph, M is not symmetric. Okay, so your point, which is absolutely right. So in fact, that's why, if you remember, for non-regular graphs, you actually don't work with M. you actually work with a normalized version of it, okay, which I didn't go over. Okay, but here right now we are just looking at assuming that we are talking about regular graphs. Okay, so MV1 is lambda 1, its first eigenvalue. Okay, let's say the largest eigenvalue. V2 is lambda 2, V2, its second largest eigenvalue, and lambda n, Vn, its nth largest eigenvalue, the smallest eigenvalue. Okay, so these are all this is what the definition of eigenvectors is, right? Everybody remember that? That m times an eigenvector is an eigenvalue times the eigenvector. So what is an eigenvector? An eigenvector is, if you think of these vectors in n-dimensional, the n-dimensional space, an eigenvector is a vector. When you apply the matrix M to a vector, you get another vector, right? So the way we can think of a matrix is nothing but an operator that takes a vector and maps it to another vector. Eigenvectors are those vectors to which the matrix sends them in the same direction. It keeps exactly the same direction, it scales them up or down. So M applied to V1 is exactly lambda 1 times V1. M applied to V2 is exactly lambda 2 times V2. M applied to Vn is exactly lambda n times Vn. Okay? For M, where M is obtained in this manner, it's not that hard. M V1 is V1. Oh, actually, sorry, I should have written the other way because I'm viewing these as row vectors, so I should actually write it the other way. Sorry about that. V1 times 1, V2 times 1. So if V1 times M is V1, what is V1? The stationary distribution. So in fact, the first eigenvector is nothing but the stationary distribution of this, okay? And this is the case if M had degeneracies, then if you had multiple connected components, then you would actually have multiple eigenvectors that are stationary. But so V1 is nothing but the stationary distribution. Good. So now, so this is what is going on. Now you recall that any vector can be written down as these form V1, V2, Vn actually form a basis for the entire space. Okay, this is something that follows from matrix theory. So any vector can be written down as a linear combination of these vectors. Okay. So what happens is that if you look at y, our vector y, it also can be written down as a linear combination of all these vectors. Of course, the first vector is u, but we know that y is perpendicular to u, so y has no component in the direction at all. So y can be written down as a linear combination of all the other vectors, ci, vi, I going from 2 to n. Okay, for some ci's are some coefficients. So y times m is equal to summation I equals 2 to n ci times vi times m. What is vi times m? Lambda I times m. So equals summation I equals 2 to n ci times lambda I. Sorry. Okay? So what's happening here is that, and I'm not going to go over the whole proof, but what's happening here is your error vector had some coefficients in each direction. Each of those coefficients got multiplied by the respective eigenvalue. Okay, so each of those coefficients got. Now, as you can imagine, and if I do the next round, what will happen? Y times m. So what do you think y times m to the t is? Ci times lambda I to the t. Okay? So what is happening is you have this vector which has components in different direction of the eigenvectors. All those components are being repeatedly, the projections on those components are being repeatedly multiplied by lambda i's. We know that this is equal to 1. We know that all of these are less than equal to 1. Their magnitude is less than equal to 1. The second largest eigenvalue, everybody else is below that, so basically what will happen is all the other components, so let's say if all the lambda i's were less than 1, this is going to get closer and closer to 0 as you keep going on. And which will be the vector that will contribute the most? The one that has the largest lambda I, because that's the one that will take the longest to go down. Okay, because so basically, imagine you started off with some directions and then you're repeatedly multiplying something by half, something by a third, something by 1/9. Then the one that is being multiplied by half again and again will stay the longest, right? So that's why the second largest eigenvalue will decide how long does it take to go down, because everybody else will be dominated by the second largest eigenvalue. What happens in the bipartite graph actually case is that the smallest eigenvalue is -1. Okay, and since we are talking about the magnitude, in magnitude this is the second largest eigenvalue. Okay, so that's what that ends up dominating. Otherwise, it's always this vector that keeps dominating. Okay, so good. So I think we made some progress on this. Any questions about this? So if you have to really, just the take-home message from here is, if you have to understand random walks, then and this is, by the way, not just for random walks, for Markov chains, you can look at the graph associated with the Markov chain, look at the second largest eigenvalue that completely captures, that to a large extent captures what is going on. Okay, so let's do I'll quickly go over the second theorem. Yes? Second largest in magnitude. Yes. Yeah. Okay. And but the point is, if the graph is not bipartite, then it is always the second largest eigenvalue that will decide. Okay. So next we are going to look at how long does it take to cover every single vertex of a graph. How long does it take for a random walk to cover every single vertex of a graph? And here I'm going to work with a non-regular graph. Okay. Before we do that, let's look at the following. What is the stationary distribution for a non-regular graph? And this is an undirected graph. Anybody remember the stationary distribution for a non-regular graph, undirected graph? Okay, again, this is something that you can play around a little bit and get a sense for it, what it would be. One can, of course, also go back to the basics, look at the matrix M, and look at some version of it that you can use for calculating this. But there is you can do an easy verification that in the stationary distribution pi for a vertex V will be the degree of V divided by 2 times the number of edges of V. Okay, let's verify it. So this is V, These are all the edges that are adjacent to it. Okay? So let's verify whether this is correct. For this to be correct, we want to calculate all the edges going into V, all u such that uv going into V, of the degree of u divided by 2m times 1 over the degree of u. What does this add up to? The degree of V divided by 2m pi of V. Okay? Good. So that is the stationary distribution. So this is the stationary distribution. So I want to find out how long it takes for me to start from a vertex u and go and cover every single vertex of the graph. Okay, so how do I go about doing this? Well, let's do the following first. So let's try to calculate how long it takes for a vertex for me to go from one vertex to another. So let's look at hitting time. Let's look at hitting time actually, or let me even look at return time. What's called return time. So let's look at h u u. Okay, how long does it take for a random walk to start from a vertex u and then eventually come back to you? Notice that this is an undirected graph, so it will eventually come back. So how long does it take to start from u and return to you? Okay, so here is some intuition. So let's say I start from u. Okay, so I start from u, I keep on going, at some point I return to u. Okay? Then I keep on going, then I again return to u. I keep on going, and again return to u. Return to u. Imagine this infinite sequence here. Okay? Let's suppose, look at this distance and let me call this x1. Number of steps it took for me to go from u to u, x1. Number of steps it took from me to go from here to u, x2. Number of steps it took from u to u, x3. So what is h u u in terms of this x1, x2, x3, x4? Anybody? Mean of the xi's. Very good. So it's nothing but x1 plus x2 and so on if I'm going up till s. Right? Everybody happy with that? What is pi u? Just looking at the sequence. So think of pi u as the amount of time, the fraction of time I spend at u. So in this sequence, I went no, I went until a certain point s. Yeah, no, so I'm looking at a one particular infinite sequence. Okay?
x1, the length of x1 itself
is random variable, but let's assume I'm taking one run, which is a specific run. So each of these is no longer a random variable. It's what I observe in that. So I observe it takes me x1 first, then it takes me x2, then it takes me x3, then it takes me x4, then it takes me. So it takes me, I go for a long period of time. I'll go until s, and think of s as very large. And in fact, ideally I should take the limit as s tends to infinity, but let me not do that for now. So I imagine s as being very long. Then I just say the hitting time must be the average of these measurements. So x1, x plus y s. Now, just looking at this sequence, what fraction of time, of the total time, have I spent at S? S by x1 plus x2 till xs. You see that? Right? Because the total length of the sequence is x1 plus x2 till xs. So what I went through S, so it's S by x1 plus xs. So really, what I have is, when of course I'm taking limits, and this is not exactly a formal proof, but I obtain that HUU is nothing but 1 over pi u. Okay? How long it takes for me to return to u is nothing but the inverse of the stationary distribution. Okay, so that's very useful, because now I know I can try to see, meaning I know a way of going from one place to another place, and I'm now going to prove that the cover time is bounded in that manner. Okay, so what I'm going to do is I want to bound the cover time. This is the expected time to cover every vertex. So what I'll do is I'll build a spanning tree, and some spanning tree. It doesn't matter how it looks like, it is some spanning tree. Okay, and imagine right now that u is here. I'm sitting at a leaf for now. It doesn't matter whether it's a leaf or not. All I'm going to do is actually bound the cover time by saying how long it takes for me to visit every vertex using the spanning tree. Okay, so it's going to be a crude upper bound, and it turns out it's actually not that crude for certain graphs, which is why we are not going to do anything more dramatic today, but it's a reasonable upper bound to work with. Okay, so let's say you have this. You start with this u, okay, and so you start with this u, and then so the question is, how long will it take before you take this edge? Okay. Well, there is lots of things going on. So notice that there are other edges in the graph. This is just in the tree that we have looked at. Well, if you are here right now, what probability are you going to take this edge? 1 by du. Good. Okay. With probability 1 over du, you're going to take this edge. But if you didn't get this opportunity to take this edge, then the next opportunity you will get after you return, which is the time HUU. How many times do you expect to return before you take this edge? So I'm flipping a coin whose probability is 1 over du. How many times do I have to flip the coin before I take that, if I get a success? Du. So the expected amount of time before I go from here to here is the degree of u times the hitting time of uu, which we calculated was 2m by du. So you can get this is to be 2m. Okay. So the expected amount of time before I take this edge will be 2m. At most 2m. The expected time of time I take before I hit this edge would be 2m. Then I do 2m, 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 2m. So I basically do a Eulerian walk on this tree. How many edges am I traversing? At most n minus 1 times 2, because sometimes I have to go back and forth. So I get and this is actually almost tight for, not up to constants, but there are some graphs for which m times n is really a lower bound as well. Okay, so it's not a terrible terrible lower bound. Okay. Okay. So no. Sorry, this is old stuff. This is just a book I referred to in case you want to look at it. Yeah. No. This is really old stuff.